we're going to go through naming and writing compounds. Now we're going to get a lot of practice at this. So this might take, that's weird. I don't know what that was. This might take a little bit of time to get used to, but I at least want to introduce it because I'm going to kind of get a lot of information here. So next part of what we're going to do, and like I said, is going to be naming and writing compounds. Nomenclature. That's what it's called. It's a fun word to say. All right, it says a binary compound is one that's comprised of two elements. Two elements. All elements in a given group have the same number of electrons in the outer shell. Now this should be nothing new to you. Elements in the same group have the same number of electrons in the outer shell. All right, and so elements in the same group must gain or lose the same number of electrons, and that should say to get. Once again, the whole point of bonding is to get a full outer shell. Right? And so, you know, if they all have 2 electrons, say it's in group 2, all elements in group 2 have 2 electrons, well, they all have to lose those 2 electrons in order for that next level to be full. All right, so they're all going to gain and lose the same amount of electrons in order to have a full outer shell, since they all have the same full outer shell. Now, a tip here is that metals will always lose electrons. Right, they will always lose electrons. Non-metals, when we talk in terms of especially of ionic bonding, will gain electrons. Because if you look at the periodic table, let me see if I can pull up the periodic table. Chemio. There it is. Once again, here we have our non-metals. These are all non-metals here that I'm highlighting. All right, these are all of our non-metals located. And they're all on the right. They all have, you know, we have some metalloids there, which we're not going to get into that, but you know, these are all the metals. All right. And so you can see the metals are located pretty much all, you know, we're going to only focus on really the, oops, you know, we might, nah, we're probably not going to look at those. We'll probably just focus on these here. And the non-metals are, we're going to focus on with ionic bonding, the metals on the far left, the blue and the purple, bonding with the non-metals on the far right, all right, with ionic bonding. All right, now the only exception to that, once again, is hydrogen up in the upper left-hand corner up here. Hydrogen is a non-metal. It's located over in group 1. That's really the only exception to that. And so, but when we talk about covalent bonding, so with ionic bonding, we're going to talk about elements on the far left bonding with elements on the far right. With covalent bonding, we'll talk about elements on bonding, you know, like carbon and oxygen bonding together. That's the atomic number 6 bonding with atomic number 8. Like something like that, carbon and oxygen bond together, like carbon dioxide. So that would be a covalent bond. When 2 nonmetals bond together, once again, when you get 2 nonmetals bonding together, or maybe like hydrogen and chlorine bonding together, hydrochloric acid gets created. So those are 2 nonmetals bonding. That is going to be a covalent bond. When you got a metal and a nonmetal, like sodium and chlorine bonding together, that's an ionic bond. And so number of electrons, once again, gained or lost to become stable is called the oxidation number. We're going to go into this a lot. So example, a sodium ion, Na ion is 1 plus. Sodium is in group 1. It is 1 plus. Oops, where's it at here? Sorry, I don't know what happened to my other thing. There we go. It has 1 in its outer shell, so if it can lose that 1 electron, the next energy level is full. All right, and so it's really it's how many electrons the atom has to gain or lose. It's not how many it has in its outer shell. All right, so the oxidation number is how many it has to gain or lose in order to become stable. All right, so like if I wrote like sodium out, once again, the sodium has 1, so it's 1. If it has 2, it'll lose 2 in order to have a full outer shell. You might be like, well, that's the same. But where you get different is like fluorine. All right, like fluorine has 7 in its outer shell. All right, but I'm not going to write 7 there because it has 7. I'm going to write how many it needs to gain in order to have a full outer shell. Once again, a full outer shell is 8. So if fluorine can gain 1, and I'm going to put a negative charge here because it's going to gain 1 electron. If it can gain 1 negative charge, it would have a full outer shell. And so fluorine's oxidation number is going to be, for our purposes, -1. 1 minus whatever. You can write it however you want. Chlorine is in the same group. If chlorine can just gain 1 electron, I'll put it like this just so it doesn't confuse you. -1, -1. Now magnesium is in group 2. So it's got 2 electrons in its outer shell. Well, it's going to be much more likely to lose 2 than it is to gain 6. And once again, we said, for our purposes, metals are going to always lose electrons. Magnesium's a metal, so it's going to have I'll write it in front, sorry. It's going to have a +2 charge if it loses those electrons. All right, because it's going to lose electrons, so it'll lose 2 negative charges, which means it'll have 2 more positive charges than negative. So that's why it's +2. Oxygen has to gain 2 negative charges. It has 6 in its outer shell. So if it can gain 2 negative charges, it will have a complete outer shell. Silicon has 4. Yeah, that's kind of a weird one. I'm not going to ask you about that, so I'm not going to worry about it. Sulfur is in the same group as oxygen. You'll notice they have the same oxidation number. Aluminum is a metal. It's in group 13. So if it can lose 3 electrons, that would be its oxidation number. All right, and so what we do when we write formulas is a pretty simple method. We use oxidation numbers to write a formula if it were to bond. So for example, sodium, let's see if I can go back to my periodic table. Sodium is in group 1. So sodium's oxidation number is 1 plus. Oxygen, if I pull up even an atomic model of oxygen, once again, hopefully you know oxygen is in group 16. Oxygen has 6 in its outer shell. Once again, you can count there. It has 6. And so, well, once again, we're not going to write 6. It has 6 in its outer shell. We want to write how many it needs in order to have a full outer shell. So sodium's is +1. Oxygen is -2. It has to gain 2 negative charges in order to have a full outer shell. So an easy way to do this, we did this with the dot diagrams. But an easy way to do this is just think how many it needs in order to gain a full outer shell. And so what you do then, after you write those charges, after you write those oxidation numbers, you simply just crisscross the number down. So I'm going to take this 1, I'll move it down here. I'll take this 2 and move it down here. It would take 2 sodium to bond with 1 oxygen. All right, because once again, and I'll explain this over here, sodium has 1 electron it can give up. Oxygen has 6 electrons in its outer shell. And so if sodium were to give up its electron, if it would get close to the oxygen would pull it away from sodium. Well, what it would do then is, one atom doesn't just come into contact with one atom. It's usually, sodium and oxygen being mixed, and so there would be other sodium atoms around. And so it would, a nearby sodium atom would come next to oxygen, and the oxygen would steal that electron also from sodium. And so it would take 2 sodium atoms to bond with 1 oxygen. All right. And once again, the other thing we talked about too is we want these numbers to equal. We want the positive and the negative to equal. All right, so you can think of it like that. So if sodium is +1 and oxygen has to gain 2 electrons, 2 negative charges, well, we got to get those to equal. So if we got +1, we need 2 sodiums. You can write it like this if you want. Sodium has to lose its electrons, so it'd be +1, +1. Oxygen is -2. And so now it takes 2 sodium atoms, a +1 and a +1. Now we have +2 for sodium and a -2 for oxygen. That's our formula there. All right, once again, I got that by looking at the periodic table and knowing how many it has. How many it needs to gain in order to have a full outer shell. So for lithium and nitrogen, lithium nitride, I'll talk about like what that doesn't say nitrogen, it says nitride. I'll explain that in a second. So for lithium, it would be once again +1 because it's in the same group as sodium. If it can lose that one electron, it would have a full outer shell. Nitrogen is in group 15, so it has 5, but once again, we don't want to put how many it has. We want to put how many it needs. An easy way to do this, I'm going to, whoops, whoa, sorry, whoa. Let me go to the periodic table. An easy way to do this also, and I'll go over this more in class, but is to put your finger on the element in question to figure out its oxidation number. You know, you can do basic math. Hey, nitrogen's in group 15. It has 5. You know, based on what group it's in, it has 5 valence electrons. It needs 8, so I can just add 3. Another easy way to do it is just count spaces, because we know that these elements, these noble gas elements right here, those all have a full outer shell. So another easy way to do it is just to count to the nearest noble gas. Because if you want it to be like these noble gases with a full outer shell, that's the purpose of bonding, is to have that full outer shell. So if you count to the nearest noble gas, that's how many electrons it needs to gain. So it'd be 1, 2, 3. That's another easy way to do it. If you don't, if you just know, hey, it's got 5, it needs to get to 8. That's one way to do it. Or you can just count to the nearest noble gas. 1, 2, 3. All right, it's 3 spaces away from the nearest noble gas. That's how many it needs in order to have a full outer shell, how many electrons it needs. All right. Doesn't really apply. You can apply that. I'll go over this more when I talk about, you can do it with the metals, but you got to go opposite. So like beryllium's in group 2, it'd have to lose 1, 2 in order for it to be like helium. So that's just a different way to figure out the oxidation number. I don't really care which method you use. Whoa, whoa. Okay, and so nitrogen we just talked about is 3 spaces away from the nearest noble gas. It has 5 in its outer shell, so if it can gain 3 electrons, it'll have a full outer shell. All right, and so that's how many it needs. It needs 3. So once again, we could either think, well, I need these positive charges to add up to the 3, or I can just crisscross the numbers. Don't take the positive and negative with it. That doesn't matter. So it would take 3 lithium to bond with 1 nitrogen. Once again, I'm going to do this just one more time just to do it, but I don't want to beat a dead horse here. So again, nitrogen has 5. 1, 2, 3, 4, 5. All right, so if lithium comes into contact, the nitrogen would steal the one from lithium, but it wouldn't stop there because it has to fill its outer shell. It's got to fill 2 more, and so it would take another lithium atom, a nearby lithium atom, it would steal its electron. It would take another lithium atom nearby, steal its electron. These would all become positive, 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 and this would become negative, have a -3 charge, and it would pull those together. And so 3 lithium atoms would bond with 1 nitrogen. All right. Aluminum, I'm probably not going to ask you these I'm going to probably stay in groups 1 and 2, but +3, oxygen -2. Once again, just looking at the periodic table, I'm going to cross them down. So it would take 2 aluminum to bond with 3 oxygen. Nice, that's all you're doing. Calcium is in group 2. Fluorine is in group 17. Once again, nearest spot away. Fluorine is right here. It's 1 spot away to neon. It's 1 spot to the nearest noble gas. So you can think of it like that. Or you can think, hey, it's got 7. It needs 8. You can do it that way. Either way, I'm fine with. Yep. Yep. All right. So you cross them down. It would take 2 fluorine atoms to bond with 1 calcium. All right. So that's how we write. And this is strictly for ionic bonds. This is the only way we're going to use ionic bonds. I'll talk about different ways to do covalent bonds. So when you see a metal and a non-metal bonding, that's what we're going to do. We're just going to use the oxidation numbers. We're going to write how many you need in order to have a full outer shell, and we're just going to crisscross. All right. Or you can do it, really however you want. If you'd rather draw diagrams and whatever works best for you. But that's only for ionic bonds. I'll talk about covalent bonds later. All right, when we write the name of the compound, we are going to write, first we must write the prefix, letters attached Well, we must know what a prefix is, excuse me. Letters attached to the front of the word. We have to know what a suffix is, letters at the end of the word. So a suffix means letters at the end. Prefix means letters at the beginning, because I'm gonna go through both of those. We'll keep the root word the same, the main part of the word the same. So when writing an ionic compound, once again, this is just for ionic compound. You always write the positive one first, all right, also known as the metal, because the metal is always going to lose electrons. So you write the positive ions first. Then you write the root name of the negative ion. So for example, for chlorine, you would write chlor. All right, and just to signify that it's part of a compound, you write IDE. So when you see like up here, you're like lithium nitride. What the heck is nitride? I know what nitrogen is, but not nitride. This just signifies when it's written as an IDE that it is part of a compound. All right, that IDE signifies, so if I said sodium and oxygen, I would say, oh, that's two separate elements. But when it says sodium oxide, that IDE tells me that it is part of a compound with sodium. All right, so that IDE just tells me that it is part of a compound. It doesn't change the element or anything like that. It just tells me, instead of saying, oh, calcium and fluorine, two separate elements. But if I say calcium fluoride, that tells me that is a bond, a different compound. It's a new compound is formed. All right, so you take the root of the word and you add an IDE. So to show a bond that is formed, you just write an IDE on the nonmetal. And so the following elements would change. If it was part of a compound, like oxygen would become oxide, phosphorus would become phosphide. Each time I'm keeping the root of the word, I'm just changing the IDE. Nitrogen, nitride, sulfur, sulfide. You get the idea. Here's the example of sodium chloride. The first name, you don't change at all. Sodium, and then you keep the second element in the compound, you keep the root, but then you change it to an IDE. Once again, that just signifies it's part of a compound. All right. Now, covalent bonds are different. Naming covalent bonds and writing covalent bond formulas are different. And so, compounds form, once again, just to recap, a covalent bond is between two nonmetals. So when you see two nonmetals, when you see two elements, let me pull up my nonmetals again. These are all nonmetals, everything highlighted here. So when you see two of these bonding together, well, noble gases aren't going to bond because they're already full for what we talk about. But if you see two of these bonding together, that's a covalent bond. So if I ask you like carbon and oxygen, you should know that it's a covalent bond because they're both occurring just on one side of the periodic table. The only exception is hydrogen, which is way over on the left. But everything else, like if I say, what's the compound for nitrogen and oxygen, you should know that it's a covalent bond, and you're going to have to know the difference. All right. So if you're looking at one side of the periodic table to the other, it's an ionic bond. If it's on the same side, it's going to be a covalent bond, with exception to hydrogen. All right. Now, covalent bonds are a lot trickier because ionic bonds, they only have so many electrons they can give up and then bond. Well, covalent bonds, we haven't really talked much about, but they can share one pair of electrons, they can share two pair of electrons, they can share three pair of electrons. And so you can get two elements bonding and have a different formula for each different scenarios just based on the type of covalent bond that formed. Like, so for example, nitrogen and oxygen can bond this very ways. You have N2O, NO, NO2, N2O5. So far, what we've learned is you would name that compound nitrogen oxide. Well, those are all very different things. They make different substances, and so we have to come up with a way to name those. And so what we do is we use these Greek prefixes. All right, once again, a prefix is something that goes in front of a word. So for example, I think I had examples here, and I don't know what happened to them. But for example, if I say, carbon and oxygen, if I say I've got one carbon and one oxygen bonded together. What that would look like, once again, that would look like, it would say, I would write this formula out. Now, you don't have to put mono in front of the first one, but the second one you do. So this would be, if one carbon and one oxygen bond together, it would be carbon. And then I'm going to use this prefix here, monoxide. Carbon monoxide. Once again, that mono signifies that it's one. So you should be able to look at the name of a compound right away and know what it's talking about. All right, how many are there of a covalent bond? All right, and so if it was one carbon and two oxygen, two oxygen bonded together, it would be carbon dioxide. Once again, the root there is dioxide. All right, or excuse me, the prefix there goes in front of, it would be 2 oxygen. All right, and so like this would be like, let's say 1 carbon and 4 chlorine. You still keep, once again, just to reemphasize, you still keep the IDE. That doesn't change. That's still something you do when it forms a bond. You still keep the IDE to show that it's part of a compound. But this would be carbon tetrachloride. So I know by looking at this right off the bat that it's tetra is 4. All right, so I know that you say carbon tetrachloride, I'm like, oh, it's 1 carbon, 4 chlorine. All right, and like these up here, I got dinitrogen pentaoxide. All right, and then this would be nitrogen monoxide. And this one right here, the one I just highlighted, would be dinitrogen. All right, so this would be dinitrogen monoxide. All right, so even though all these other examples I gave you didn't put, there was no prefix in front of the first, well, if there's 2 there, like there is here in that first one, you got to put the prefix there. If it's only 1, like these are all 1, that's 1, that's 1. You don't have to put mono in front of the first one. I'm not really sure why, but that's just the way it's kind of written. But for this one and this one, it'd be dinitrogen monoxide, dinitrogen pentaoxide. All right, once again, just using those prefixes. So we'll get plenty of work at this. We'll get plenty of practice. I'm going to give you a compound, and I'm going to say write the bond, write the name out, which is, so if I give you, if I give you CO2, and I say write the name of it, you'll say, well, it's carbon dioxide. Or I'll give you carbon dioxide, and I'll say write the formula. You have to tell me it's CO2. All right, and this is only for, once again, this is only for covalent bonds. So when they're bonding on the same side of the periodic table between nonmetals. All right, that's a wrap. Get out of here. Oh, long video. Sorry about that.